So, a couple of housekeeping issues. First off, remember that homework, we're collecting homework next week, Thursday. So, you'll have 6 homeworks due next week, Thursday. You got blue yesterday, you got yellow today, and then you'll get the other 4 as we go along throughout this unit. Okay? But those will all be due on Thursday of next week. Okay? Also, you probably found out today in homeroom that your final will be on day 1 of finals, period 2. Okay? So make sure you write that down. That's for everybody. Day 1, period 2 for finals. 3:15. Okay? You got it? Okay. Well, welcome. No, I am for real life. Okay? Alright? So we got that going on. Okay? So that's everybody up in 3:15 then. Okay? So make sure that you have yesterday's white sheet out, because we're actually going to start by talking about yesterday's white sheet here momentarily. Okay? So, yesterday we learned about different types of data and some of the ways that we can organize them. Okay? Again, it's going to be a video. It's a video presentation to get you through the statistics part. Okay? A quick hitter, a quick dipping of the toes into the statistical world. Okay? One of the things that we need to talk about in terms of that is we need to talk about the shapes and what we can get out of a normal curve or a normal a distribution, a shape. Okay? So, this is the front side of yesterday's white sheet, just so you know. Okay? The following normal curves represent battery lives. Battery lives. Okay, good, it's working. They represent battery lives of populations, or of a population of cell phones of comparable models from different companies. What can we say about the mean battery lives between the 2 models? Okay? Well, the mean battery life, or the mean in a normal curve, is at the peak of the curve. In the earlier class, they were saying that it's at the middle. Okay? It's not in the middle. Okay? Because if your data is skewed, okay, so if my data is skewed to the left, okay, so there's my data skewed to the left, the middle would be right here. Okay? But the mean is actually right there. Okay? So we can't just say that it's in the middle of a curve. On a normal curve, yes, we can say it's in the middle because a normal curve is symmetrical on both sides, and so the mean and the median are right there. Okay? So in the mean of these 2, let's take a peek at them. So let's drop a little from the peak, let's go straight down there. And from the peak, let's go straight down there. What can you say about the means of those? Now, we're assuming that we have the same scale going on between these 2. Okay, what can you tell me about the mean? It's what? So the means are roughly the same, right? Okay, so the means here are roughly the same. Standard deviation, okay? Now if I'm talking about standard deviation, the taller the curve, the smaller the standard deviation. So the taller the curve, the smaller the standard deviation, the less spread out your data is. Okay? Yesterday in one of the videos that we got to towards the end of class, they were talking about Wahoo Tacos. And they had 2 locations that they were talking about. One was in a mall with a controlled environment, all that stuff. One was at the beach where you're kind of weather dependent, temperature dependent, all that stuff. Okay? So the weather dependent, the beach one, had all of its data, its 12 months of data, and it was all spread out in the stem and leaf plot. Okay? Whereas the mall was all tight. The data was all nice and tight, grouped together. Okay? So the taller the curve then, the more tight, compact your data is. Okay? The larger or the shorter the curve, the more spread out your data is. So what can you say about the standard deviations of the 2 models? Well, A here has a taller curve. So the data is more compact, and the standard deviation is less. B would be just the opposite. Okay? So B has a short curve, which means spread data, which means a larger standard deviation. Okay? With that in mind, now, what I would like you to do is I'm going to give you a minute to answer those 2 questions about 3 other cell phone companies, A, B, and C. So what can you tell me about the means of the 3 different batteries? They are not the same. They are different. So what can you tell me about them? What can you tell me about the 3 means?
They're like equals 1, 2, 3, 4, and then that's the mean of the A, and then 4 more, so they're equal distance apart.
So they're about equidistant apart? Yeah. Okay. What else can you tell me? That's not a mean, though. KG? So when you guys say it, you guys are gonna go, well, duh. You guys are, it's great. You guys are going like next level. But what can you tell me about them though? I get that they're all different. No, they're not exactly the same. Because you just said that they were different. And now 5 minutes later, or not even 5 minutes, a minute later, you're changing. But I'm not talking about the curves. I'm talking about the means. Which one's bigger? C is bigger, right? Okay. What comes next? B. What's the smallest one? A. Okay. So C is the biggest. Austin, why is it the biggest? Because it's the furthest to the right. Exactly. Okay, so C is the biggest because it's the furthest to the right on the graph. Which one's the smallest then? A. Why is A the smallest? and B is somewhere in the middle, right? Okay. Okay, so if we drop those, if we drop these, the peak would be right in about here, the peak would be right in about here, and the peak would be right in about here. Okay? If we assign numbers to the bottom ones, we could get what those numbers are then, right? Okay? Now let's talk standard deviations. What can you tell me about the standard deviations now of them? Max.
They're all the same.
Why are they all the same?
Because they're all on a level plane. They're all the same size.
Okay? So the curves are roughly the same size.
Each of the mean has 3 dashed lines to the left and right for all.
That's means though. I'm not talking that. We moved on to standard deviation. Yep. Okay? So the curves are roughly the same size, so that means we have 3 roughly the same standard deviations. Okay? I would agree with that. Okay? Because we have 3 equal curves, okay? The standard deviations are roughly the same. Okay? So, what we're going to do today is we're going to watch the next video here. Okay? Next party video, yeah. Okay? And we're going to talk about some more measuremental type stuff. Okay?
Hi, I'm Bertie Savetti, and this is Against All Odds, where we make statistics count. Histograms are pretty much old hat by now. You know they're a great way to graph the distribution of the sample values for one particular quantitative variable. Size of gala apples at one local orchard? Here's your histogram. Math SAT scores for entering students at a state university? Here's your histogram. Percent of senior citizens in the U.S. population over the decades? Here's your histogram. To make it even easier to focus on general shapes, sometimes statisticians draw a smooth curve through a histogram. This can help us spot similarities in shapes, even when the histograms we're comparing don't necessarily have the same source or scale. You might notice something about the smooth histograms in our example. The apples and the test scores result in roughly the same shaped curve, though of course the data sets are completely unrelated. This special shape is called a normal curve. It's symmetric with one peak, what we call bell-shaped. The mean, mu, and the median are the same point, right here in the middle. Lots of distributions in the natural world exhibit this so-called normal curve shape, as we can see on a visit to Manomet Center for Conservation Sciences, located on the shore of Massachusetts.
This is a sort of a central for migration of anything can be coming up our coast.
Since 1970, biologists here have been tracking migratory birds as they pass through every spring and fall. 50 mist nets spread out over the property and snare birds when they come down to rest or feed in this attractive seaside habitat. Researchers quickly work to disentangle the birds and head back to the lab to measure and record all the vital stats.
We is 61, Rock 5, Jersey B0BP, Orwell, we scroll.
Each bird also gets banded. A little anklet that contains identifying info is placed on its leg, so anyone who catches this bird again, whether at Manomet or as far away as South America or the Arctic, can learn more about where it's traveled. Over the decades, the scientists have banded thousands and thousands of birds and collected tons of data points before sending them back on their way. Here's a histogram built from the wing lengths of all the great catbirds they measured since 1970, and another for all the great catbird weights. And take a look at one more, which tracks how many white-throated sparrows get banded each day of the fall migration season. Recognize anything special here? We can draw a normal curve over all 3 examples. The bars in the histogram represent the actual sample data the the researchers collect from the birds they capture. The curve represents our idealized assumption of what the whole population of waits would look like for every catbird that passes through Manomet, whether captured or not. It's based on the actual data. An important feature of any normal curve is the fact that it's completely defined by its mean, mu, and its standard deviation, sigma. If you change the mean, the whole curve just scooches along the x-axis. If you change the standard deviation, you're changing the distribution spread, and the peak gets flatter and wider, or taller and narrower. The Manomet bird records allow scientists to build a comprehensive picture of how bird migration has changed since they first started collecting data.
We actually track it down to the number of nets that were open, the number of hours, so that we have a birds per net per hour figure. And by 1995, we were catching half as many birds as we were in 1970. So we saw a 50% drop over 30 years.
Much of that decrease in the bird population can be chalked up to habitat degradation and loss. If there are good places for the birds to live, eat, and breed, they won't survive. What's unique about the Manomet record is that it lasts all the way through each migration season. That provides researchers with much more info than a commonly collected piece of data called first arrival.
Birders, bird watchers, they go out each year, and often what they're most interested in, what they record, is the date that they see the first bird of a species each year. So first date is interesting and important, however, it can be very variable with changing population sizes. So that's what makes these data from Manomet so valuable, is that we also have mean arrival, which is less susceptible to changing the population size.
Check out these normal curves showing migration data for the black-polled warbler. The y-axis measures the number of individual birds observed. In year 1, many more birds were caught at Manomet, which you can see from the higher peak. By year 33, fewer birds were passing through. What's interesting is that while the mean stayed the same, the first bird now arrives later in the season. That's a function of the population shrinking. Smaller populations are harder for researchers to keep tabs on because the individuals are comparatively few and far between.
With a smaller population size, it becomes increasingly difficult to see that first bird, so that's why we see it later.
Here are the curves for another species, the eastern towhee. Again, the y-axis describes the number of individual birds observed. You can see the population decrease for these guys too, based on the lower peak in year 33. What's different here is that the first arrival was spotted about the same time over the decades, and the mean of the distribution has shifted earlier. If you only know the first arrival date, you wouldn't have a clue that the mean arrival has shifted. Something's affecting migration timing for this population as a whole, most likely climate change.
If it's a warm year and plants leaf out and flower early, then maybe insects will also emerge early, and then ideally the birds would arrive early so that they can take advantage of the insects and the food sources that are available. So if those events become out of sync, if the birds are not arriving earlier in a warmer spring, they can suffer as a consequence.
It's easier to make comparisons on the eastern towhee data if we convert each bell-shaped smooth histogram into a normal density curve. To do this, we change the scaling on the y-axis from a simple count of the number of birds observed to a relative frequency, or proportion. With this new scale, the total area under the density curve is 1. Even though these curves are based on different numbers of birds, the area under each density curve represents 100% of the birds in each sample. Now we can compare the proportion of birds that arrive by a specific day for year 1 and year 33. It's obvious the mean for year 1 is later, with the whole curve moved along the horizontal axis to the right. The curve for year 33 is a bit taller and pointier because the data that year is less spread out, with a smaller standard deviation. And you can see that those first arrivals are happening at just about the same time. What's different between the 2 years is the proportion of birds that have arrived by a particular time. year 33, half of the birds had arrived within 48 days of the spring equinox, while in year 1, only 0.23, or 23% of the birds, had arrived by that time. In year 1, it was another week until half the birds had arrived, at 55 days after the equinox. Here are the density curves for the Blackpoll warbler, with its consistent mean over the years, and its later first arrivals. From the density curve, we can compare the proportion of birds arriving by a certain day. Let's pick day 56. In year 1, the area under the curve is 0.10, meaning 10% of birds had arrived by this date. In year 33, the area under the curve is 0.04, meaning only 4% of the birds had made it. So the percentage of birds that used to arrive by day 56 is more than double what it is now. In both years, half the birds had arrived by day 67. The only thing causing the observed later first arrival is that fewer birds are migrating, making it tougher for researchers to spot the rare birds. Remember, it's the observed first arrival. A bird or two can easily sneak in under the radar, so to speak, unseen by researchers. The scientists at Manomet say it's important to take into account population sizes when looking at migration times, especially if the only data available are those easily influenced first arrival dates. Fewer birds could mask the reality that while the first bird is being spotted at a consistent date, a far larger percentage of the population is arriving earlier. You don't want to base important conservation decisions on misleading data. Luckily, things are looking up for some of those birds after the rough decades of the 80s and 90s.
The conservation policies both at the national and international level, the fact that people are learning more about birds and preserving habitat in their backyards, even at the smallest level, people are putting out bird feeders in the winter. And so for a variety of reasons like those, we found at least for the last 15 years that all bird populations are level. This does not mean that some are not declining, and those are the ones we should be concerned about, but it does also mean that some are increasing, and that is good news.
A nice silver lining for some of our feathered friends. See you next time. I'm Party Sabetti.
Alright. Okay. So, talking about normal curves now. White sheet for today, backside, you're going to want to take some notes down here and now on this stuff, okay? Because she talked a little bit about the empirical rule, okay? Which means, okay, that if I take a standard normal curve, okay? So you're going to want to draw yourself a standard normal curve, make it a little bigger, make it a little bit bigger. It's one of the few notes you're going to take today. Okay? What that does, or what that standard normal curve does, is it takes and it divides up right down the middle. So 50% of my total data is on this side of that peak, which means that 50% of my other data is on the right side of the peak. Okay? Because the mean and the median in a normal curve are the exact same. Okay? So 50% are on either side. Which then, if we go out one standard deviation, okay, if we go out one standard deviation, then that puts 68% of the data in between there. Which means that 34% of the data is above the mean to that one standard deviation line. Which means that 34% of the data is below the mean up to one standard deviation. Because there's 68 total percent in between there. Now, if we take that out one more standard deviation, now there's 95% of the data between each of those. This one, this one. So that means then again there was 50% over here, and there's 50% over here. So now that means that there's going to be, well, what's 95 divided by 2? 47.5. So that means that in here, there is 47.5% of your data on both sides of there. Okay. We go one more standard deviation. Now there's 99.7%, okay, which means basically you have all of your data within 3 standard deviations. Because on this side, it was 50%. This side, it's 50%. Well, so what's that? 90 or 40, so 99, 45, 49.35. Let's go with purple. Okay. Now, if we put all of those together onto one curve, okay, we get this breakdown. And unfortunately, maybe I can make this be a little bit bigger. Okay, so then you get this as a breakdown. So this would be a, oh, that's my inflection points. Got it. Okay. So in all told, you've got if you're going above and below, this is a nice one that you want to make sure that you have written out because it breaks it down for you. Okay. It breaks it down for these percentages. We'll get into using this a little bit more tomorrow, too. Okay? So this is a nice one. So this says that this middle line right here, that was our median. So what this is saying is that there is 34% one standard deviation off the median. Then between the first and the second standard deviations, there's 13.6%, which you would have gotten if we would have subtracted these two. 47.5 minus 34 is 13%, okay? Which is where they're coming up with this numbers, okay? Then between the second and the rest of the data, there's 2.5%, or 2.15, excuse me, percent. Okay? All told, you've got the empirical rule. Okay? Now, rough estimating. How do we find those standard deviations? Well, when you're looking at a normal curve, it's just a little bit above the halfway point. If I were to put a dot kind of right in there, that would be almost the halfway point from the peak, okay, the midpoint there. It's just a little bit above. It's just a rough estimate. Okay? So now, if you take on the front side of your white sheet, okay, so we've got two different normal curves. Okay? the first thing that you need to do is you need to find where the peak is and then drop a line down. So roughly, where is the mean of the math SAT scores?
500.
It's roughly at 500. Remember, I'm letting you know this because you're going to see this in the next video. The mean symbol is mu. Okay, looks like that. It's a funky looking U. Okay, but we found that to be at 500. Okay, now we look at, try and find the standard deviation. Well, the halfway point is probably right about there. I go a little bit above the halfway point. So that's there. And now I drop a line down from that. Whoa, whoa. I don't want that one. I want this one. There, that's what I want. Oh, come on now. I want it. Alright, caramba. I'll go over here and I'll move it up from over here. Okay, so we drop that down. So roughly, what is the standard deviation? The standard deviation is the distance between that, where we drop that line down, and the mean. So in this case, in this first one, my standard deviation, which is, the symbol is a funky O. Got all these funkiness. What is the distance from mean to standard deviation? About how much? Just 100, right? Because this is at 500 and we're going to about 600. So I would say the standard deviation here would be about 100. Agreed? Okay. What I'd like you to do now is I'd like you to find me the mean and the standard deviation for the tree diameters. What do we get for the mean of the tree diameters? About 11? Okay, I would go with 11 more than I would go with 10. Okay, because we go from the peak and down, I would go, looks to be more 11-ish than 10-ish. Okay? Standard deviation. What did we come up with for a standard deviation? So if my mean is at 11, my standard deviation drops down to be about 14. So I get there a standard deviation of 3. Agree? Yeah? Speak now or forever hold your peace. Okay? All right. Next video today, we'll be talking about z-scores and how we relate standard deviations and how we can compare them.
Hi, I'm Hardy Sabetti, and this is Against All Odds, where we make statistics count. Normal can be kind of a tricky term. Remember, it's special statistical meaning. It has nothing to do with whether you're an ordinary Joe or a freaky oddball. In statistics, a normal curve is symmetric, single-peaked, and bell-shaped, and it's completely described by its mean and standard deviation. Normal curves have a unique feature that can be summed up by what's called the empirical rule. It's also known as the 68, 95, 99.7 rule, and here's why. About 68% of the observations will fall within one standard deviation of 99.7% of observations will be within 3 standard deviations of the mean. The standard deviation is a natural yardstick for any measurements that follow a normal distribution. Take a look at the range of heights for all American women. Symmetric? Check. Single peaked? Check. Bell-shaped? Check. The mean, mu, is here at 63.8 inches, and the standard deviation, sigma, is 4.2. That means the average woman's height is 5 foot 3.8 inches. We can measure out with our yardstick. 1 standard deviation from the mean in both directions takes us to 68 inches on one side and 59.6 on the other. So 68% of American women are between 4 foot 11.6 and 5 foot 8. Let's measure out another standard deviation with our yardstick. Now we're 2 sigma out from the mean in both directions, bringing us to 72.2 inches and 55.4 inches. That means 95% of American women are between 4 foot 7.4 and just over 6 feet. We can take it 1 more standard deviation out to 3 sigma. Now we wind up at 51.2 and 76.4. 99.7% of American women, the vast majority, are between 4 foot 3.2 and 6 foot 4.4. Only 1/3% of women, just 3 in 1,000, are out here at the extremes, shorter than this or taller than this. Life out of the extremities of a normal distribution can sometimes feel a bit lonely, hence the existence of the Boston Beanstalks. We dropped in on a recent get-together of this club for tall people.
The person wants to join the club. We invite them to one of our social functions. And if we know they're coming, we have a tape measure ready. We put them against the wall, we put a little mark on the wall and measure it.
The tape measure must read 5'10" for women and 6'2" for men to gain admittance to the Boston Beanstalks. These requirements make sure only the loftiest segments of the general population make it into the club. A member's first exposure to a tall club meeting can be quite a departure from the world these tall folks encounter every day.
Thank you, everybody.
At the end of the night, my neck really hurt, and I couldn't understand why. And finally, I realized because I wasn't looking down. I was either looking even or up. I was the shortest person there because it was mostly guys, and they were all like 6'7", 6'8".
Instead of having the conversation be about a foot below me, where I couldn't hear it because of the music from the dance, I was able to talk to people.
In my whole life, I was always the tallest one, so I could see the entire room and everything around me. And for the first time, I had that feeling of the intimacy of a dance floor when you have people that are all the same height around you or taller than you. It was an amazing perspective change. For the very first time in my life, I felt like I belonged in a group, like this is where I am supposed to be.
At the national average height for women of about 5'4", our producer was looking pretty shrimpy compared to the Beanstalks in attendance at this dinner dance. The club offers a convivial atmosphere where members can enjoy temporarily being in a place where they are typical height and meet others in the same shoes.
Being in the grocery store and having someone ask you to get some on the top shelf, or, it's always about reaching for something.
We actually have had members thrown off the plane because they couldn't fit behind the seats.
One of the members of the talk club has built his own house, and he has all of the counters about 4 inches higher than normal. He says that he used to have back pain all the time, but as soon as he put in the raised counters, he stopped having the back pain.
But overall, these Beanstalks are proud to be tall and love hanging out with their compatriots in the club.
It brings such a variety of people together. It's such a large group. It's such an amazing group of people that I can't recommend anything higher than trying to get into a group where you can be part of this. And for us, it's the tall girls.
The minimum Boston Beanstalks height requirements are 5'10" for women and 6'2" for men. These standards seem at a first glance to be reasonable for a tall club, where members are aiming to socialize with the literal upper tiers of society. But just how far above the mean must one be to gain access to the Boston Beanstalks? If we look back at our normal distribution of women's heights, to a standard normal distribution. Setting its mean at 0 and standard deviation at 1, almost all the data that falls between -3 and 3. In this case, the observation we're interested in is the 70-inch height requirement. So 70 is our x. We know from before that the mean mu is 63.8, so we can add that to our equation. And sigma we know is 4.2. Do the math, and we have a z-score of 1.48. Well, that's great, but what the heck does that mean? It means that a woman who just meets the minimum club requirement of 70 inches has a standardized height of 1.48, or 1.48 standard deviations above the mean. Z-scores can be negative too, if they represent an observation that is below the mean. How do the gentleman beanstalks stack up against the general male population? Just plug in their numbers to the z-score equation, and we can see that the 74-inch requirement for membership is 0.98 standard deviations above the mean. A standard deviation of 0.98 is pretty darn close to 1. Think back to the 68, 95, 99.7 rule, and we can estimate just how much of the male general population is eligible for beanstalk membership. 68% of heights are within 1 standard deviation. That leaves 32% of people further away from the mean. 16% are shorter than 1 standard deviation away, and 16% are taller. Based on our 0.98 z-score, we're approximating that 16% of American men are up to snuff in the height department, at least as far as membership in this club is concerned. But since we actually have a precise z-score, we don't have to estimate. We can calculate the percentile that's the actual cutoff for beanstalk membership. There are 2 ways to do this. You can turn to a z-table, which lists how much of the distribution falls below any given z value. In our case, we look up 0.98 by locating 0.9 to the 10th place on the vertical axis, and 0.08 for the 100th place on the horizontal axis. And that gives us 0.8365 as the proportion of heights that are lower than 6'2". In other words, 83.65% of American men are too short to join up with the beanstalks, meaning 16.35% of American men make the cut, so to speak. That's pretty darn close to our estimate using the empirical rule. Alternatively, you can use software to calculate these percentages directly without using a z-score at all. What's helpful about z-scores is they allow you to compare observations from 2 different normal distributions by standardizing them with a common scale. For instance, we can compare the eligibility requirements for male and female Boston beanstalks. With the gents at a minimum z-score of 0.98 and the ladies at a minimum z-score of 1.48, we can see that the height requirements are actually more stringent for female beanstalks. They're half a standard deviation further from the mean than their male counterparts. The height cutoffs are kind of a historical accident, left when all the tall clubs around the United States joined together in the 1940s. But maybe it also helps keep the genders equally represented, since some women may be more motivated to hang out with taller men than vice versa. We can also use these scores to compute the percent of data that falls in the interval between 2 observations. Let's say we want to know how much of the American population is taller than I am, but still not tall enough to make it into the Boston beanstalks. Basically, we want to know the percentage of area between 2 points. Calculate the z-score for my height, 64.5 inches. It's 0.16, just above the mean at 0. We already know the z-score of 7 inches, the beanstalk cutoff. It's out here at 1.48. Looking at the proportions in the z-table, I see that 0.9306, or 93.06% of American women, are shorter than the shortest Boston beanstalk. I'm pretty close to the mean, with 0.5636 or 56.36% of women shorter than I am. Subtract the 2 areas and you can see that this chunk, taller than I, but shorter than the club members, is 36.7% of the population. Well, I'm pretty sure that I stopped growing a long time ago, so the Boston Beanstalks is one club that won't ever accept me as a full-fledged member. For Against All Odds, I'm Party Betty. Steve.
All right, so 2 things you should have gotten out of that video, okay? First off, What is a z-score? Anybody? We got it. Yep. How many standard deviations the data is from the mean. Now, she went kind of fast on this one, but how do we find z-scores? Well, the z-score is equal to, I take my data point and I subtract off the mean, and then I divide that by the standard deviation. Okay? She had it in the video as x minus mu over sigma. Okay? Same thing. Okay? If you just want to write it down, data minus mean over SD, that's fine. That's probably the easier way for you to remember it. Okay? So, front side of the white sheet now, we've got to decode some information in order to figure out a z-score. Okay? Because then we can use that z-score to compare it with other things. Okay? It standardizes everything. It takes whatever data we have and it makes it nice and standardized, so I can compare it to somebody on this one to another study that might have been done the previous year or something like that. Okay? That allows us to compare. Okay? So the mean cholesterol level of adult women is that. So that is my 188 is my mean. With a standard deviation of 24. Okay? The question is, find the z-score for a woman with a cholesterol level of 212. So that would be my data point. Yep. Okay? So my z-score is going to be data minus mean divided by standard deviation. Right? So that is, data was 212 minus mean is 188 divided by standard deviation of 24. 212 minus 188, 24. 24 divided by 24 is 1. So that person is, or that woman is 1 standard deviation above the mean, because she has a z-score of 1. Okay? You calculate now the z-score for a woman with a cholesterol level of 174. So my data point was 174 minus 188 over 24. That gets me negative 14 over 24. So my z-score here was what? Negative 5?
Or
Negative 0.583. Okay, does that make sense? Can z-scores be negative? Yes, that means that we are below the mean. Okay, which we should have known. We should have gotten. Hold on, don't be packing up yet. That's just rude. Okay, we looked here and we saw that our z-score was 100, or not our z-score. Our data point was 174. Our mean was 188. So that's below the mean, so we better get a negative z-score. In the first one, we were above the mean, so we get a positive z-score. Positive z-scores are above the mean, negative z-scores are below the mean. Okay? Yellow homework is tonight's homework. I wouldn't wait until next week, Wednesday, to do it. I would still do the homework, even though it's not due until Thursday.